interactive session. So today we have planned with certain specific chapters. So last class nama panna kudiya adhe chapter dan, that is what I have planned for today as well. That is electricity is what we were seeing. So a chapter which plays a vital role for competitive exams. So last class we have seen certain concepts. I had briefed up on certain concepts, and today we are going to dive into the question part. Okay, different types of questions. We looked at easier questions in the last class based on conceptual uh, topics that were addressed. So let me start sharing the screen. So just let me know if you're able to see the screen which is being shared. Yeah. So I've started sharing now. So I hope you're able to see the blackboard. Okay, where I explain the concepts. You're able to see it. These were the concepts that which I explained in the last class. So this is the new screen that I've opened. Okay, fine. So we'll look at a quick recap of what we have learned so far, and then we'll proceed further so that there is continuity. Okay, so we'll have a quick recap. So first and foremost, the basic formula which we learned pertaining to electricity was the basic formula for electricity. Yeah, the important concepts, definitions, and formula. The first one is electric current. So we can say electric current is nothing but the rate of flow of charges. So I is equal to Q upon T, where Q is charge in coulombs and T is time in seconds. This is the first and foremost. Further, you can also write Q or charge as n times electrons, integral multiples of electrons. It can be expressed that way also. So I'll just make a note of that also on the screen. So we can also write Q is equal to Ne. So I'm writing that here. Q equals N into E, where N is an integer number. It can be any integral number, integral value, and E is the charge of an electron. So who can tell me what is the charge of an electron? What is the value? The value for E?
1.6 into 10 to the power of minus 19.
Correct. 1.6 times 10 raised to minus 19. So we can express charge, electronic charge, as multiples of electron charge. Okay, that is 1.6 times 10 raised to minus 19 into any particular integral value. 5 electrons, if you say, it will be 5 times this value. If you say 10 electrons, it will be 10 times this value. As simple as that. Okay, so that's the first and foremost formula. Now going to the second formula, this is the first one. Now going to the second one, it's electric potential difference. It is defined as the work done to bring a charge from infinity to a point against electric field. So you try to do a work in bringing a charge. Then the work done in bringing the charge from one point to another, you say that as electric potential or electric potential difference. In short, we can say V is equal to W upon Q, where W is work done in joules and Q is charge in coulombs. So this is the second formula. Quite simple, it's easy and understandable. Third, very important, Ohm's law. Ohm's law is quite simple. It gives you a relation between potential difference and current. So we say electric potential difference is directly proportional to the current passing through a conductor, provided temperature is going to be constant. So we can say V is proportional to I. When you remove the proportionality sign, you introduce a proportionality constant, and we call that as your resistance. Okay, so hence we get the relation V is equal to I into R or R times I. Okay, where R is your resistance. The unit of resistance is ohms. That's the symbol which is shown below. Okay, and then you have grouping of resistors. So there are two different types of grouping. You can group resistors in series and you can also group them in parallel. So first, what do you mean by series combination? Series combination is when resistors are grouped one after the other, just like how you have the compartments in a train. First you have the engine and then you have all the compartments that are connected. That's a classic example of series combination. Okay, so that's how you can easily visualize series combination of resistors. Okay, where each compartment in a train would refer each resistor. Okay, so R1, R2, R3, so on up to Rn, when they are connected in series, the effective resistance is simply the algebraic sum of individual resistors. Okay, so just you need to add them. That will give you the total resistors in series combination. Now, two important points that you will have to note in series combination is that the current passing through each resistor is same. So I is same. Okay, because it is a single wire where you're connecting all the resistors. So the current passing through the first resistor would pass through the second, through third, fourth, so on until the last resistor. Okay, so current is same, but what about the potential difference? The potential difference across each resistor, if you're going to take a voltmeter and going to check or measure the potential across each resistor, it would show you a different reading. So the potential difference is going to be different, but current passing is going to be the same for series combination. So I is same, but V is different for series. Okay. Now coming to parallel, you can see how resistors are connected. Here resistors are connected in, across each other. Okay. They're not connected one after the other, but they are connected across each other. Just like how you can, find them in a ladder. The connection of sticks in a ladder is a classic example of parallel combination. Okay, so that's how they are connected. This is called a combination where it is connected across. So all the resistors R1, R2, R3, so on up to Rn. In parallel combination, if you're going to find out their effective resistance, very simple. You take the series, you just need to apply reciprocal or inverse of the series. Okay, so 1 upon R effective is equal to 1 upon R1 plus 1 upon R2, so on up to 1 upon Rn. So you just need to take the reciprocal or the inverse of series, you would arrive at the formula for parallel. Now coming to parallel, there are two important points the same way as I told in series. What are they? In parallel combination, what can you say for current? Is current same or is it different? The current passing through each resistor.
Different.
Yeah, current is different, but potential is same. Okay, the potential difference is same across each resistor in parallel combination. So this is a golden rule that you will have to remember. The rules pertaining to parallel combination. It's exactly the opposite of series combination. The current passing through each resistor is different, but the potential difference across each resistor is ultimately the same. So this is all about parallel combination. Okay, so this is all we learned, and also a few more concepts I had taught. The other concept is, I'll just scroll down. We looked at certain questions. Yeah, then we looked at what is resistivity, that is rho. Okay, the formula for resistivity also was taught. So how do you write the formula for resistivity? We can write rho is equal to RA upon L, or you can say R is equal to rho L upon A. Now here rho is called resistivity, L is your length of your conductor, and A is nothing but the area of cross section of your conductor. So technically speaking, resistance is directly proportional to the length, meaning you increase the length of the conductor, so does the resistance of the conductor. So what is resistance? It's the opposition to the flow of current, which you guys already know. Now similarly, resistance is also inversely proportional to the area of cross section of the conductor. That means you increase the area, the resistance would decrease. That is why we call it inverse relationship. Okay, so if area increases, the resistance will decrease. That's the reason. Have you seen the thickness of the wire used in your laptop charger? Have you seen your laptop chargers? The thickness of the wire, right? You compare that with the thickness of the wire used in the air conditioner. Now, who can tell me which has got a lesser resistance? Your laptop wire or the air conditioner wire?
Air conditioner wires.
Exactly. Why?
Sir, it has larger cross-sectional areas.
Exactly. It has a larger area of cross section. Now, why do you think they are designed in such a way that they have a larger area of cross section? Because their power consumption, power need is more. Okay, the current requirement is more. When can current flow at a greater rate? When there is a lesser resistance. When can there be a lesser resistance? When the area of cross section is greater, okay, or it is more. That is the reason the thickness of the wire used in air conditioners is technically greater, or it is typically greater than that of the laptop chargers. Okay, this is something that you can keep in mind, so it's easy for you to correlate with real life examples. So with that we move on. Then we have temperature coefficient of resistivity, okay, which is given by the relationship rho t is equal to rho naught times 1 plus alpha delta t, where alpha is your coefficient of resistivity, okay, and rho t is nothing but the resistivity at final at final temperature t. Rho naught is resistivity at initial temperature t naught, okay, and delta t is change in temperature, which is final minus initial temperature. So again you have this relationship. And then we learned about conductance and conductivity. Now, conductance is nothing but the reciprocal of resistance, which is 1 upon R. It is represented by the letter G. Okay, it is also called as Simon, or it is Mho. It is the reciprocal of resistance, hence the name. Same way, conductivity. So that is nothing but the reciprocal of resistivity. It is represented using the symbol sigma. So sigma is 1 upon rho. So whose unit is ohm inverse, meter inverse, or Simon meter inverse. So these are the units. And then moving on to power. Power is defined as the rate of doing work. Okay. So there are different formulas for power. 3 formulas are there. It can be written as a product of potential difference and current, which is VI. It can also be written as the square of current times resistance, that is I square R. It can also be expressed as the square of potential difference upon resistance, which is V square upon R. So there are 3 different formulas for power. And the SI unit for power is watts or watts. Okay. And then you have Joule's heating. So Joule's heating is again given by the relationship heat is equal to power into time. Now, heating is basically a phenomenon that is observed in electric appliances when you're using them for a considerable amount of time. It can be your food processor, it can be your television, it can be your laptop, your mobile phone, any electrical appliance or gadget that you're using for a considerable period of time is going to consume power, and so thus is going to get heated up. You would have observed sometimes a longer usage period would definitely result in a heating effect. That is called Joule's heating effect. Okay, so it is given by the relationship power into time. So you substitute the formulas for power, you would arrive at the heat formulas. So heat can be expressed as VIT, I square RT, and V square upon R into T. So there are three different formulas. And how do you express the unit of heat, the SI unit of heat? We express it as joules. So that is the unit of heat. And then we have electric energy. Now, electric energy is also expressed as power into time. It is the same thing. And here, except for the fact that power is expressed in terms of kilowatts, there it is just watts, but here it is expressed as kilowatt or kilowatt. Okay, so in domestic circuits or in domestic usage in our house, when we have so many appliances that are consuming power on a daily basis, we get a monthly electricity bill. So the monthly electricity bill is based on the number of units of electricity that we are consuming. Okay, so 1 unit of electricity technically means 1 kilowatt hour of energy consumption. Okay, the electric energy consumption. So if you are using based on the number of kilowatt hours, the number of units at the end of the month would be generated, and your bill also gets generated accordingly. So it is based on the kilowatt hour, which is your commercial unit of energy. It is the unit used to identify the consumption of a particular consumer or a customer on a monthly basis. Okay. So here we have the conversion from kilowatt hour to joules. So 1 kilowatt hour is technically equal to 3.6 times 10 raised to 6 joules. So this is a conversion from kilowatt hour to joules. Okay. I hope you guys are aware that kilo means 10 to the power 3. That's the reason we call a kilogram as 1000 grams. Again, 10 power 3 grams. Okay, so that's a quick analogy. We had a quick summary of what we have learned so far. Okay, with that, we are proceeding further. Okay, and now we are moving on to an important concept, which I'll just explain it to you, and then we will see all the different types of questions that are possible from the competitive point of view. Okay, so now here comes two important major concepts, so which is called as the Kirchhoff's current law and the Kirchhoff's voltage law. Okay, so there are two concepts that we need to know. So let me introduce you to that. So first concept, let's see, which is Kirchhoff's current law. Okay, now what we try to understand by Kirchhoff's current law. So it is also shortly referred to as KCL. Okay, so KCL stands for Kirchhoff's current law. So the person is named, after this rule. So this rule is named after the person who has actually found it out, Kirchhoff. So we'll see what is this Kirchhoff's current law. What does it mean ultimately? Okay. So according to Kirchhoff's current law, it tells you that the sum of the currents entering a node or a junction equals the sum of the currents leaving equals the sum of the currents leaving a node or a junction. Okay, so Kirchhoff's current law tells you that the sum of the currents which are entering a node or a junction is equal to the sum of the currents leaving a node or a junction. So we can also say that sigma I is equal to, that is entering inside, input we can say is equal to the sigma I output. Okay, so the sum of all the currents entering a particular node or a junction is equal to sum of all the currents leaving the node or a junction. For example, if we try to represent this using a simple diagram, so I'll just draw a simple diagram, just show it to you. So we have a resistor, say this is R1, and there is current I1 here, and you have another resistor, say R2, which is carrying current I2. Okay, you have another resistor, say R3, carrying current I3. So now all three of them are meeting at a point as shown. Okay, say here I have current I4, this is I6, I7. Okay, so I have expressed like this. Now, how do we try to relate? You can see that there is a node or a junction situated here. Let me call it X. So X represents a node, or X can be called a junction. So how do we apply Kirchhoff's law here? Okay, Kirchhoff's law can be applied at this particular junction. So based on the number of currents that are entering or the number of currents that are leaving. So how can we express? We say the sum of the currents entering is equal to the sum of the currents leaving. So who can try and tell me what are the currents that are entering here? The current entering X input currents?
Sir, I1, I2,
I1. Yeah, so we can write it as I1 plus I2 plus I3. What else is entering? There is one more also. You can see I4 is also entering. So plus I4 is equal to, now what are leaving? There are two currents that are leaving X, which is I6 plus I7. Okay, so this is how you write down the expression for the Kirchhoff's current law at a node or a junction. Okay, this is the method to write it. Okay, so this is one of the laws. Is it clear, or anybody's got a doubt? I hope this part is clear to all of you.
Yes, sir.
Yeah, this is your Kirchhoff's current law. Okay, so this is again, necessary whenever you find a node or whenever you find a junction in a particular circuit. So you can see that the sum of the incoming currents is always going to equal to the sum of the outgoing currents. Okay, this is the first law that I have taught for the day. That is Kirchhoff's current law. Quite simple. Now I'll introduce you to the second law. The second law is called as Kirchhoff's voltage law. It is also called shortly as KVL. Okay, so that is the second law. Let me just write it here. The second one is Kirchhoff's voltage law. It is also called as KVL. Now, what do you mean by KVL or Kirchhoff's voltage law? Okay, it states that the sum of the potentials, the sum of the potential across the sum of the potentials across each component in a closed loop or circuit is always equal to 0. Okay, it tells you that the sum of the potentials across each component in a closed loop or a closed circuit is equal to 0. Is it clear, children? This is what is Kirchhoff's voltage law. This is what Kirchhoff's voltage law tells you. The sum of the potentials inside a closed loop or a closed circuit is always equal to 0. Okay, this is how we represent Kirchhoff's voltage law. Fine. So this is the method to, this is a statement for Kirchhoff's voltage law. Now I'll give you a simple, example. So first I'll write the general expression. So sigma V inside a closed loop is equal to 0. Sigma means summation. Okay. So I'll just give you a simple circuit. Okay, so we have a circuit like this. All right, so let me call this as V1. Let me call this second cell as V2, the potential, and I'll give you the resistors also. So say this is R1, say this is R2, this is R3, R4, R5, and R6. Okay, so these are all the resistors. Now, we are going to assign the direction of current. Okay, very important. Please, pay attention here. So whenever you have a circuit like this, the first and foremost thing that you would do is to identify the nodes in the circuit. Okay, or to identify the junction in the circuit. Now, what do you mean by a node or what do you mean by a junction? Can anybody tell me? What do you mean by a node? Yes? Identify the nodes or junctions in the circuit. Okay. Okay, that is step 1. So we are doing a step-by-step analysis. Okay. The first one I will show you. You can tell me from the second, figure. For this figure, I will tell you. I will guide you guys. No worries. So for this circuit, now I told you step 1 is to identify the nodes. Now what is a node? Node is basically a point in a circuit where 3 or more components meet or 3 or more wires meet. Can you see that there are 3 wires meeting at this point? Can you observe? I have highlighted. So this is basically a node. So I will mark it as say x1. Okay, so it is a node. Why it is a node? Because 3 wires are meeting there. You can see that 3 wires or 3 components are basically meeting, and hence I am calling that a node. Similarly, there is another node also in the circuit. Can you see? Exactly opposite to x1, there is one more node. Okay, this is another node. Why you call it this as another node? Because again, there are 3 components meeting at this point. So this is another node, say x2. Okay. Now, apart from these two, do you have any more nodes here? Are there other nodes apart from x1 and x2 in the circuit? Just see. Can you find? Apart from x1 and x2, do you have more nodes in the circuit? It is just 2. No, exactly. You don't have any more nodes because there are only 2 nodes. What about these 2 corners? You cannot call them nodes because 3 components are not meeting. It is just 2 parts which are meeting. Okay, it is just a single connection basically. Okay, not even 2. It is just a single connection. Fine. So therefore, you cannot call it a node. Okay, that is just an end of the loop. So I can just name it as A, B, C, or so on. Okay, so let me call this as A. This part you can call it as B. This end I can call it as C. A, B, and C are not nodes, wherein x1 and x2 are only the nodes. Okay, this is the first step that you will have to do whenever you get a circuit like this. Okay, step number 1 is now done. We have identified the nodes in the given circuit. Now moving on to the second step. Step 2. In step 2, what we are going to do is you are going to assign the direction of currents. Okay, you will assign the direction of currents based on cells or batteries given in the circuit. Okay, this is the step number 2. So here what do you understand? Based on the given cell or a battery, you are going to now assign the direction of currents in the circuit. Very important. This is step 2. First, you identify all the nodes. Second, you are going to assign the direction of currents based on the cell or battery in your circuit. Now, how many cells or how many batteries are there in the circuit? By just looking at the circuit, you can tell me. How many are there?
2, sir.
Yeah, there are 2 cells, which is first cell is V1, the second cell is V2. So you have 2 cells. So we will start first with V1. First, what you do, you are going to mark the terminals of both the cells. You know the bigger line is positive, smaller line is negative. So mark the terminals. And then you are going to now assign the direction of current. Now who can tell me how does current flow outside the cell or battery? From which terminal to which terminal it flows?
Negative to positive, sir.
Negative to positive. Okay, that is for inside. Outside, it is always going to flow from positive to negative. Inside the cell or inside the battery, what you said is right. Negative to positive. Okay. But outside the cell or outside the battery, it is going to flow from positive to negative. Always remember, current will only flow from higher potential to lower potential. So positive potential, that is positive plates, is at a higher potential. So therefore, it flows from positive to negative terminal. Is it clear? So it will flow from positive to negative. So now I'm going to assign the direction of current. Let's say the current coming from V1 is I1. So how does I1 flow? I1 will flow like this. Okay, towards the left of the positive, it is going to flow. It will flow through resistor R1. It will flow through resistor R2. But will it flow through resistor R3 directly? Will I1 pass through R3?
No, sir.
No. Why? Because there is a node in between.
I1
Now
should be,
this
sir.
correct. So now I1 is not going to pass through R3 because there is a node. So therefore, in the node, it can either split, okay, or it is going to get divided. So we are going to now see that. Okay, we are going to identify it. Now I1 we have shown. Now there is another cell also which is V2 in the circuit. For that also we have to now assign the current, isn't it? So we are showing that current as well. Now the current coming from V2, we will mark it as I2. So this is I2. You know current flows from plus to minus. So I am showing this I2. Now who can tell me what is the current passing through R3? Apply the
I1, I2, sir.
exactly. Which rule we are applying?
Kirchhoff
Kirchhoff.
current rule, sir.
Yeah, we are applying Kirchhoff's current rule. Are you understanding? Because there is a node X2, the currents coming from R2 and current coming from R3. Okay, so they both are joining at X2 and they are passing through R3. So at R3, the current passing is I1 plus I2. Okay, so that is the current passing through R3. The same current will also pass through R4, which is I1 plus I2, because both are in series combination. I told you in series combination, current is same, isn't it? Even R1 and R2 are in series. That is why the same current is passing through them. Okay, R3 and R4 are also in series. So the current is same. Okay. Now, next what happens through R6? Who can tell me what is the current passing through R6? Resistor R6. Here.
I1, sir.
Yeah, it is I1. How are you telling it is I1? Because the
Kirchhoff
current,
current rule.
yeah, Kirchhoff's current loop. You can see I1 plus I2 is entering from R4. But through R3, I2 is leaving. So you will subtract it. I1 plus I2 minus I2. So therefore plus I2 minus I2 cancel. You will only be left with I1. Okay, which is the current which is passing through. Now you can see that I1 current only is passing through R1 also. So what we have done is absolutely right. The distribution of currents. Are you understanding? This is how you are going to distribute the currents real time. Whenever you get a circuit, you are going to first identify the nodes or junction. Second, you are going to provide the direction of currents based on the cell or battery that is there in the circuit. Okay, so we have assigned the direction of currents now. So step 2 is also over. Next,
Sir,
step 3. Yes, yeah.
sir, what is to R5, sir? Is that also I2, sir?
Yeah, that is also I2. Okay.
Okay, sir.
Yeah, that is I2 only. Okay, because you have V2, so obviously that is going to be I2. Okay. Yeah. So step 1 is done. Step 2 is also done. Step 3. Next step. Step 3, what you will do? You are going to now apply KVL. KVL inside closed loops. Inside the loops. And KCL at nodes. Okay. Step 3 is you will apply KVL. You will write the equations for the loops and you will apply Kirchhoff's current law at the nodes. This is step 3. So here, how many equations you will write for the case KVL? How many loops can you see in this circuit? Loops are nothing but the closed circuits. How many loops are there? How many closed circuits can you find?
2, sir.
Yeah, you can find 2 loops. What are they?
ABC X1, sir.
Huh. Okay.
X1, X2, C, sir.
Yes. You can call it as AB, X2, X1, and A. Finally, X1, X2, C, and X1. Okay. So this is one loop, and this is another loop. So there are two loops. For each loop, you can apply the Kirchhoff's voltage law, which tells you the sum of the potentials inside the closed loop is always equal to 0. Okay, so there are two loops. So now we are going to apply the Kirchhoff's voltage law for the loops. Okay, so applying KVL in loop 1. So loop 1, how do we address loop 1? Always start from a point and you will have to again come back to that same point. A, B, X2, X1, A. So I started from A and again I will come back to A. Only then the loop is complete. Okay. Again I'm telling you, you will start from A, B, X2, X1, A. Okay, that is the first loop. So I'm writing it here. A, B, X1, X2, A. So this is a closed loop, first loop. Okay, for this loop, now we are going to apply the Kirchhoff's voltage law. According to Kirchhoff's voltage law, because I am starting from A to B, do you find any component between A to B? There is like resistor, capacitor, or inductor, okay, or cell or battery. Nothing is there between A and B. Okay, so we need not write anything for A and B. Now move from B to X2. Is there a component between B and X2? You can see that there is a resistor R2. Okay, so how will you write the expression for potential? Now, how are we moving? We are moving in the same direction as current. Okay, so whenever you move in the same direction as current, and when you encounter a resistor or when you encounter a cell or a battery, you need to understand you have to use a positive sign convention. Okay, when the current is as the same direction in the circuit and you are also moving in the same direction, you will use positive sign. So between B and X2, how will I write the expression? You will write it as R2 into I1. So first R2 I1, then I am again moving. I am now touching X2. From there, I will move X2 to X1. Now X2 to X1, there are two components. What are they? One is cell V2, one more is resistor R5. Okay, there are two components. Now, you can see that as you are moving in the opposite direction of current. Current is I2, which is coming, but we are moving in the opposite direction of current. But I am now first encountering a cell. Now always remember, for cell the rules are, if you touch the positive terminal of the cell, you will use positive sign. If you first touch the negative terminal of the cell, then you apply negative sign. So as I'm moving from X2 to X1, which terminal of the cell am I touching for V2? Is it positive or negative? As you are moving from X2 to X1, which terminal of the cell are you touching first?
Positive, sir.
Exactly, positive. So I will use positive sign convention. So I will write plus V2. Okay, plus V2. And then how am I moving for R5? Am I going in the same direction as current or opposite direction of current? When you move across R3, I mean moving across R5. Sorry.
Opposite direction, sir.
Yeah, opposite direction.
Opposite direction.
So how do I write it? I will use a minus R5 into I2. Have you understood? Resistance and current is nothing but the potential difference. V is equal to IR, isn't it? So therefore, I am writing minus sign. Why minus sign? Because I am moving in the opposite direction of current as I touch resistor R5. That's why minus R5 I2. Now I have reached point X1. Now again I have to come back to A from where I started initially. Between X1 and A, how many components are there? You can see there are three components: resistor R6, cell V1, and resistor R1. So there are three components. So can you try and tell me the equation now between X1 and A? First, what will you write? How am I moving?
To the direction of current,
Yes,
sir.
in the direction of current. So what will be the first expression? It will be,
Plus I1 or 6.
yes, plus I1 R6, plus I1 into R6. Okay. Then next you are touching a cell. So what will be the, how are you going to write the expression?
Minus V1.
Yeah, just minus V1. Potential only we are writing. So minus. Why minus? Because we are touching the negative potential as we are moving. Can you see? It is a minus sign. So we are writing it as minus V1. Okay, minus V1. And then the next one. For R1, how will you write?
I1 R1, sir.
Yeah, it is I1 R1 plus only because again in the same direction. Okay, plus I1 R1. Okay, now have we come back to the same point from where we started? Yes, so we have come back to point A. So the sum of all the potentials in the closed loop is equal to what? It is equal to 0. So this total thing is equal to 0. This is how you are going to apply Kirchhoff's voltage law inside the loop. Okay, I hope it is clear. Okay, now sometimes it might be confusing, but once you understand the rules, it is very, very simple. Okay, now the same way, shall we try to apply it for the second loop? What is the second loop here? It is x1, x2, c x1. Okay, so I want you to try it again. So now we are going to apply, that is applying KVL in loop 2, which is x1, x2, c x1. Okay, so can you tell me the expression for x1, x2, c x1? How will the expression go? Yes, one of you try it. Between x1, x2, there are two components. One is resistor R5, one more is cell V2. Yes, come on children, just give it a try. It's easy. What is the expression?
Sir, I2 R5 plus.
Yes, I2 R5 plus, is it plus after I2 R5? That sign is plus. That is what you meant, I think. Okay, plus I2 R5. Okay, then
Minus V2
very good. Minus V2.
plus I1 plus I2 R3
Yes, plus R3 times I1 plus I2. Okay,
plus R4 times I1 plus I2.
yes, R4 times I1 plus I2. Okay, that's it. We have come back to point X1. Simple. So this is the expression. Okay, so we are moving in the direction of current. So therefore, plus sign for all the resistors and the currents except for cell V2 because you are touching the negative terminal of the cell V2. That's it. These are the expressions. Okay. So let me write down here. So for that, I need to first check. Yeah. So it is I2 into R5. Here it is I2 R5. Then minus V1. And then we had plus I1. I suppose it is I1 plus I2, right? Yeah, I1 plus I2
Sir, minus V2, sir.
plus R minus, okay, minus V2, my bad. Okay, minus V2. Okay, plus I1 plus I2 into, what was that resistor? R3, small r, anyways I put capital R here, nothing wrong. R3, then plus I1 plus I2, R4. Okay, into R4. Let me use small r itself to avoid confusions. Okay. That's it. So like this, you are going to write the expressions for loop 2. Okay. So this is how you apply the loop laws, that is Kirchhoff's current law and Kirchhoff's voltage laws. Okay. So here what we have applied is your Kirchhoff voltage law. Inside the closed loop, you will use KVL. At your nodes or junctions, you will use KCL. Okay. So I hope now it is clear, children. I have given you the basics, okay, of the loop laws, Kirchhoff's both current laws and the voltage law. Now shall we see questions based on this? Okay. I hope you guys are ready. So now we will go ahead with the different types of questions. Okay. Here comes the first question. I'll just give it to you. Yeah, so first we'll look at this question. Yeah, here comes the question. The current passing through resistor R2, okay, through R2 is, options I will give you. First I will draw the circuit, okay. Okay, the first one is actually R1, this one is R4, and this is R3, this is R2, which is 100 ohms. Okay, this is cell E1, which is 50 volts. This is cell E2, which is 20 volts. Okay, so you have to find out what is the current passing through R2. Okay, that is the question. So I am giving you the options. Option A, 312.8 milliamperes. Option B, 300 milliampere. Option C, 311.8 milliampere. Option D, 300.8 milliampere. So these are the options. So you have to find out what is the current passing through R. So as I told, first and foremost, you will mark all the nodes in the junction. So apply the step-by-step procedure that I taught you. Okay, take your time and tell me the answer for this circuit. So mark all the nodes and then you can assign the direction of currents, and finally you will frame the equations, you will solve the equations and get the answer. Okay. There are two different approaches for this. The first approach is what I have taught you. Okay, that is a general CBSE approach. Okay, so NCRT based approach is what I have taught you. One more is a competitive approach. Now, competitive exams, because of the time constraint, there is another approach where you get the answer very fast. Okay, I will teach you that also. But first, I want you to try. I want to check if your concepts are first clear. So use the conventional approach, okay, which I have taught you, the traditional way. Do it and tell me what is the answer that you're getting. Okay. So before you tell me the answer, I would like to know what are your equations, because this circuit has got three loops, right? So for all the three loops, I want you to tell me three equations. If you are getting the equations right, obviously your answer also will be right. Okay, that way I can verify. Okay, so first you show the direction of currents and then you try to tell me the equations for all the three loops. Okay, that is your primary approach now. I hope you guys are trying it. To do it, I'll give you, 2 to 3 minutes. You can try it. I want you to write the equations. Okay, and meanwhile, I'll have some water and come. Just give me, a minute so that you can also, write it down in the meantime. Yes, children. So I'm back. So have you found out how to write the equations for this loop? Have you assigned the direction of current? Anybody has tried it out? Yeah. So from which cell have you started? Anybody who has started, you can tell. So I will also start from the same cell.
Sir, E1, sir.
Okay, you have started from E1. Yes. Why it is good to start from E1? Why not E2? E2 also you can start, no doubt. But always give more preference to the cell that is having a higher potential. Okay. So this is a small tip. Whichever cell has got a higher potential, you start from that cell. Okay. Yeah. So we are also starting from E1. Okay, fine. So first I will mark the polarities. Now what is the current supplied by E1? I hope you have taken it as I1.
Yes, sir.
Okay, so this is I1. Okay, done. So I1 is entering through R1. Now you can see that here there is a node. Okay, so let me mark the nodes. First step was that. So this is one node X1, another node X2. Okay, this is another node X3. Finally, the last node X4. Okay, so there are 4 nodes in the circuit. Okay, yeah. So I1 is there. Fine. So that we have marked. I1 is entering node X1. Okay. Now between X1 and X2, actually you don't have any components. Okay. So technically speaking, X1 and X2 nodes can also be combined because you don't have any other component in between. Okay. So you don't need to have a gap there. Okay. That can be joined. X1 and X2 can be joined. Same way X2, X3 and X4 also you can join. Okay. But what we do if you're going to join X1 and X4 and X1 and X2, you can reduce the resistors because they're in parallel combination. But we cannot do so because the question is demanding us to find out what is the current through R2. So we cannot afford to reduce the circuit further. Are you understanding? So therefore, we keep it as it is. Just X1, X2 can be combined. Okay. So that can be done. So now what we do here, we are showing now what is the split up of the current through nodes X1 and X2. So node X1 and X2 can be treated as one itself. These two can be treated as one super node. Okay, you are treating this as one particular super node. So the entire thing, so X1 and X2. Okay, so I will write it as X1, X2. So I am treating it as one super node. So now it is the current either has to enter the node or it has to leave this node. Now, based on that we can only decide based on the current that is coming from the other cell, which is 20 volts. So again, mark its terminals, show the direction of current. So from E2, let's say current I2 is coming. Okay, you can see I1 is coming from cell E1 and I2 is the current, incoming current from cell E2. Now both of them are encountering the super node X1, X2, and obviously they are going to leave the nodes as well. Okay, current entering the node has to be equal to the current leaving the corresponding node. Okay, so that also you can show it. Okay, the sum of the currents entering is going to be equal to the sum of the currents which are leaving. So that also you can show it. Fine. So how you are going to show it is the question. So I1, where you current passing through R2. What is the current passing through R2? Anybody? Because you're treating it as a single node. So how do you show it?
Sir, I1 plus I2 by 2, sir.
I1 plus I2 by 2. Why is it I1 plus I2 by 2?
Sir, it not need to be.
Okay, because it will not be exactly half, no, because R2 is different, R3 is different, both are not same, isn't it? So it will not be exactly half the amount of currents which are going to flow. So here is where you will have to be very, very careful. So whenever you're writing the currents through any particular resistor, especially when they are in parallel combination, so what did I teach you? You will going to use the current divider rule or the current divider method here. Okay, and then you are going to write it. So further this circuit, you redraw the circuit again. So let's redraw by simplifying our circuit. Okay, so now when you're going to redraw the circuit, how your circuit is going to look? Okay, how is it going to look like is what we are going to now see. All right, so I will show that one. So when I redraw the circuit, my circuit looks like this. So this one was R1. Okay, and X1 and X2 I am combining. Okay, so then I am having, what is that, R4. This is R4. After that, here I had one cell. Okay, one cell was there. Now you are going to show both the resistors. Here one resistor is there. Here there is another resistor. Two resistors. Are you understanding? So I am showing it like this. I have now reduced that node because it is common. And this is your second cell. Okay, so R1, R4, this is R2, and this is R3. Okay, and this is E1, I suppose, and this one was E2. And we also show the currents by based on the polarities we have shown. So say this current is I1, and what is this current? I2. Okay, this current is I2. So this is what we have seen so far. Okay, so this is what we have done so far. Now we are showing the amount of currents that are going to pass through each of the resistors. Now these resistors that you have found here in this circuit, okay, now instead of showing them in terms of I1 and I2, we have to represent them using another variable. There is no other option. Okay, because the currents are anyways going to enter through R1 and R2. We are not really sure about the currents, whether it is going to be I1 only or I2. So we are not getting into that. Okay, some of the currents we know it is equal to the sum of the currents leaving a node. Some of the currents entering a node is equal to sum of currents leaving. That much we definitely know. Are you guys understanding? So therefore, we would represent them using another variable. Say out of I1 and I2 which is entering, say we have I3 which is leaving, which is passing through R3. Okay, so I3 is passing here. Then what would be the amount of current passing through R2? Anybody? If out of I1 and I2, I3 amount is going through R3, so balance how much will go through R2? It will be
I1 plus I2 minus I3.
exactly. It will be I1 plus I2 minus I3. That's all. That is what I am writing. I1 plus I2 minus I3. Okay, through R2. Okay, so like this we are writing. That's it. By the time it comes here to the other node, so say this is your super node X1 and this is another super node X2. So by the time it comes to X2, you now know what is going to happen. Both of them are going to join, and appropriately here how much is going to flow, here how much is going to flow. Here again they are going to split, and I2 will start flowing here. Okay, and here also by the time it joins, you know that I plus I3 minus I3 will get cancelled, and I1 plus I2. So out of that, I1 is flowing towards the left, I2 is flowing towards the right. That's it. Okay, like this you show the splitting. Once you have shown the splitting, as I told you, now you will apply the loop laws. How many loops can you see visually? How many loops are you are able to see in the circuit? You are able to see how many loops? There are 3 loops, if you can observe. Are you able to see that there are 3 loops? First loop, this is second loop, this is third loop. So like this 3 loops are there in this circuit. Okay, so that is your identification. From here you know now how to apply the loop laws and how to get the expressions. Okay, so now let us try to apply them and write the equations for each one of them. So when you write the expressions for each one of them, you will get 3 equations. Now 3 equations in 3 variables, you can solve them, you can simplify, and you can get the answer. That is one approach of solving. Okay, solve the system of linear equations in 3 variables, solve them by using elimination method, substitution method, whatever method you know you can apply, and you can simplify, you can get the answer. That is how we do it traditionally. Is it clear? That is a general method. Now we are going to see another interesting method of how to find it rather than using the traditional method. What are the other ways of approaching this question? What is another method of doing this question? General method. Now if you do like this, you will be spending another 2 to 3 minutes extra on this sum to solve. Okay, but in competitive exams, we don't have that much time to invest on each question, because the number of questions and the given time, you will have to use a quicker approach to solve it. So now we are going to see what is the quicker approach. How can we solve it even more faster? That is what we are going to see. Okay, fine. So let me now show you that. Okay, so now I will just erase certain things here to make the circuit much little clear, so that I will explain that method here now. Okay, till this circuit, I hope things are clear to you guys. Okay, so this circuit is now clear. Now to this circuit, what I am going to do is, listen carefully. We are aware about the nodes in the circuit, and the common nodes we have simplified as x1 and x2. Now that is what we have done. Okay. And which are the resistors that are in parallel here? The resistors that are in parallel here are two resistors. What are they? R2 is in parallel to R3. Do you agree with me? Both of them are in parallel. So when I say parallel, what is the meaning? The potential across R2 and R3 are exactly the same. Okay. This implies V is same. For what? For R1, that is for R2 and R3. Now, do we know that potential? We don't know. Let us assume that potential as V. I am marking in that figure. Let us say potential across R2 and R3 is V. So I am writing it here. Potential difference across R2 and R3 is V. Now, how can we write the equation directly? Okay, if you assume that potential across R2 and across R3 is V, okay, now we are going to understand certain things. Okay, now apply the positive and negative terminals for your potential. Potential difference means obviously it is a combination of plus and minus. Where it is plus, where it is minus. How do you identify? Can you see the flow of current through R2 and R3? How the current is flowing? Current is flowing vertically downward. Now, what does this mean? You know that current always flows from higher potential to lower potential. Have you understood? So, X1 is typically positive, X2 is typically negative. Is this clear? So, you first mark this. You try to understand this first. Okay. So we have understood that R2, R3 are in parallel. Potential across them are same. And the potential terminals also we are trying to mark. X1 is positive, X2 as negative. Why? Because current is passing vertically downwards. Therefore, X1 has to be positive, should be at a higher potential, and X2 should be at a lower potential. That is what we have marked. Now I am going to write the expression. Okay. Now when I write the expression for the entire potentials in this circuit, now you see, you can see that here when I'm going to express. So first, let me try to write down the entire potential. So let's move on. So here you can see that there is cell E2. We can start from either of the sides. Okay. And we can write it. So which one is the values of E2 and the values of E1? So E2 I think was a smaller value, I guess. E1 was more. E2 is 20 and E1 is 50. Okay. So E2 is 20 and E1 is 50. 50 volts. Okay. Now there are two ways, sides to this. So first, if you're starting from E2, now E2 is plus 20. Okay. So 20. Now across R4 and across R3, now you can see for R4, if I'm going to write the equation, how can I write? Okay, one by one, for each resistors, one by one we are going to write. Okay, so across R4 you have 20 volts, and for X1 the voltage is nothing but V, and we don't know that corresponding value, and current is passing from 20 towards X1. Higher potential is 20, the lower potential is X1, so it is passing from 20 volts to X1, and the amount of current we know it is, say, I2. So when you write the equation for purely potential, we can say 20 minus V divided by the resistance, because V by R is nothing but current, right? So 20 minus V divided by, which is that resistor that is involved? It is R4. Okay. So I am writing that. So 20 minus V divided by R4 is equal to, why I'm saying equal to? Now because it is again getting divided across the node, is equal to. So how much is passing for R1? Okay, or you can also say plus R1, because we have assumed there as current which is entering from R1. Okay, so you can also write plus also, no worries. Okay, because that is also entering. So let me put a plus sign. That is how we have assumed. So plus for R1. How can we write for R1? You can see that is 50, and at x1 it is v plus. So how can we write the expression? 50, yeah, 50 minus v, right? So plus 50 minus v divided by which resistance is there between 50 volts and x1? It is R1. So divided by R1. Okay, these both are we have put. Okay, yeah, these both now is equal to, now they are leaving through R2 and R3. Okay, now the current is going vertically downwards, so we can say, so the potential there also, the potential across x1 and x2 is purely v. So how can you write it? You can say it is v by R2 plus v by R3. Directly you can write it. See, over in one step we are able to write the expressions. Substitute the values. 20 minus v divided by R4. What is the value of R4 from the question? R4 value was, I hope it is 30, right? Yeah, 30 ohms by 30 plus 50 minus v divided by R1. What is the value of R1? It is 20 is equal to v divided by R2. R2 is how much? 100 plus v divided by R3. R3 was 120. Okay. Now everywhere on the left side and the right side, what can you do? Can you cancel off the zeros? 110. Is it possible? Yes. Can we do that?
Yes,
Yeah.
sir.
Yeah, very well you can do it. So 20 minus v by 3 plus 50 minus v by 2 is equal to v by 10 plus v by 12. So we have to rearrange for now v. The expressions needs to be rearranged and you have to find out the value of v. So how do you find out the value of v? Either you can go by the method of LCM. It is totally your lookout. Okay, you can go with LCM or any other approach. Okay, so I would recommend you, instead of going for LCM, multiply with that LCM directly. So who can tell me what is the common LCM of the numbers 3, 2, 10 and 12? What is the LCM of 3, 2, 10 and 12?
30, sir.
30. 12 does not go by 30, no?
60, sir.
60, yes. So 60. So multiply with 60 throughout. Okay. So 60 value to be multiplied with the entire thing. Okay. This entire whole value. So if you do that, what are you getting? 60 by 3, 20, right? So 20 into 20 minus v plus 60 by 2 is 30. So 30 into 50 minus v is equal to 60 by 10 is 6. So 6v plus 60 by 12. How much is 60 by 12? 12 5s are 60, right? 5v. Okay. So this is how you write it. Okay. Now again simplify. 20 into 20. What is 20 square?
400, sir.
400 minus 20v plus 30 into 50. 1500 minus 30v. Okay. And is equal to 6v plus 5v, which is 11v. Okay. Club all the v terms together and go for a simplification. Okay. So again, 400 plus 1500 is 1900 minus 30 minus 20 is minus 50. Okay, minus 50v, it's a variable, is equal to 11v. So minus 50 can be taken that side. 1900 is equal to 50 plus 11. How much is that? 61v, right? So so v is equal to, what is the value? 1900 divided by 61. So find out the value. You should get it in decimals or something. So 1900 divided by 61. How much are you getting? 31 point something. 31.14 volts. Okay. So this is the value of potential. See, we have got the potential now directly across those resistors. Once you have got this potential, okay, now you are going to find out what is the current. So what will be the current passing through R2 directly? Now you can find current passing through I2. You can apply the Ohm's law. I is equal to V by R, right? So I through R2 will be equal to V divided by R, the value of R2. How much is V? 31.14. Divided by how much was R?
100, sir.
R was 100. Okay. So divided by 100. Okay. Divided by 100. So how much is the answer? 31.14 by 100. It is in terms of milliamperes you have to say the answer. So it will be 311.4 milliamperes. Okay. So you get the answer as 311.4. Okay. So like this we have found out the answer for this circuit. Is it clear? Okay. So approximately we have done it and we have found out the corresponding answer. Is it clear? So this is the approach to solve this type of questions. You can solve it in just one go based on this type of analysis. Instead of going with conventional way, don't you think this is easier? You can get the answer much faster. Okay. So this is the approach to find out the current. Whenever you have bigger, circuits, and they are asking you the current through one of the components, you will apply. You will apply this, and you will do it this way. Okay. Yes. One of you have a query, you can ask. Yeah. Any doubts?
Sir,
Yeah.
sir, here R1 and R4 are parallel, sir.
R1 and R4. R1 and R4 are in.
Are in series, sir.
No, they are not in series. How are you establishing that they are in series? In between R2 and R3 is also there, no?
Oh,
Okay.
sir.
Yeah. So you cannot say that they are in series. Okay. Series means they should be one after the other without any branch in between. If there is no branching and if directly they are connected, only then you can call series. But here you have a node in between, so it is not possible to say it is in series.
Okay.
Okay. Yeah. Fine. Is it clear, children? All of you? I hope it is. This part is clear, right? So this is the approach to solve the question. We have looked at a higher level question from the competitive point of view, and we have solved it. Okay, using a simple approach. The same way you can do it for the other questions also. Okay. So we can do one more question also, but because of the time constraint, we are not able to do it. Okay, I'll give you the questions for practice. Practice sums I will give. I will post it in the group. So you can practice and get back to me in case you have any queries. Okay, next class we will see even more questions and then we'll move on further. Okay, to forthcoming topics. All right. Yeah, any doubts you can ask based on today's lecture. Any more doubts? That's it. Is it clear to all of you?
Yes, sir.
Okay, very nice. Great. All right. So then we'll meet up in the next, lecture. Okay. So we'll see as many classes are kept because you guys also had your exams and we could not have the classes in between. I think sir also has posted that in the group. So we'll try to accommodate as many sessions as possible and we will try to cover up the syllabus for you. Okay. So I'm there to help you out. Okay. So I think there is no queries. Shall we wind up? I suppose sir is also there.
Thank you, sir.
Yeah, yeah. Welcome, welcome. Bye bye, children. Take care.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you,
Okay,
sir.
welcome.
சார்
எஸ் எஸ், ஏதாவது டவுட் இருந்தா கேட்கலாம். எஸ்
சார் இந்த லெசன் இல்ல, இந்த லெசன் இல்லாம எனக்கு ஒரு ஒரு டவுட் இருக்கு சார்.
சரி கேளுங்க.
சார் ஃப்ரீக்வன்சி இன்வெர்ஸ்லி ப்ரொபோர்ஷனல் டு டைம்ல சார்.
ஆமா
சார் அதே மாதிரி வெலாசிட்டியும் இன்வெர்ஸ்லி ப்ரொபோர்ஷனல் டு டைம்ல சார். v ஈக்குவல் டு எஸ் பை டில.
v is equal to s by t, பட் இன்வெர்ஸ்லி ப்ரொபோர்ஷனல் எப்படி சொல்றோம்?
சார் அதாவது நம்ம ஒரு மணி நேரத்துல
velocity வந்து is inversely ன்னு சொல்ல, see you cannot say it is inversely proportional to சொல்லலாம், பட் கான்ஸ்டன்டா always displacement need not be constant, it can change based on the path that you are taking, so it is really difficult to establish that relationship. Okay,
சார் அப்ப அது இன்வெர்ஸ்லி ப்ரொபோர்ஷனல் டு டைம் கிடையாதா சார்?
inversely proportional to time கிடையாதா அப்படின்னா you cannot say it is faster, so time might be less or time might be more also, depends on the rate at which you are traveling, அவ்வளவுதான். ஓகே, ஸோ velocity and time are inversely proportional, எஸ் சொல்லலாம். ஃபாஸ்டர் நீங்கள் சீக்கிரம் நம்ம ட்ராவல் பண்ணுறோம் அப்படின்னா the time will be less, அவ்வளோதான். greater the velocity lesser will be the time, அப்படி சொல்லலாம். ஓகே
சார் கான்ஸ்டன்டா இருந்தா அது வந்து இன்வெர்ஸ்லி ப்ரொபோர்ஷனலா தானே சார் இருக்கும்?
எஸ் எஸ் எஸ், inversely by the expression போனீங்கன்னா yes it is true. Okay, so if you want to see the exact meaning, faster we travel lesser time is taken, so yeah inversely is also true. yeah சொல்லலாம்
சார். அப்போ வந்து சார் ஒரு நிமிஷம்.
ஓகே
எல்லாமே நம்ம என்னடா டெம்பரேச்சர் தான்.
ஆமா.
அது விஜயமானம் தான் எல்லாமே. சரிடா சரிதல்ல.
ಚೆನ್ನಾಗಿ ಓಕೆ ಮನೀಶ್.
ஓகே
ಮನೀಶ್ ಓಕೆ.
யா
ಓಕೆ ಓಕೆ